Okay, so today I will discuss the topic is about generalized linear model. Okay, so I think this is a very important issue for modeling our interest and some covariates, that is regressors. Okay, so let's start to the next page. At first, I introduce our dataset in this chapter. This dataset is about the Boston HMDA dataset. Okay, so we focus on some variables. And at first, we should import this dataset. Okay, so this dataset is about it's a data file. So we should import this file from this package. This package is named foreign. So if you don't install this package, you should write down the install package at first. Yeah, you should type it here. Install package. If you don't install this package in the past, you should install it at first. And you should use a quotation mark. Okay, so if you don't install this package in the past, so you should write down in R. Okay, so and then I set out my path for this file and import this dataset from the read.dta command, and you can import this command in R, and you are successful. So you can successfully import this dataset. Okay, so at first we should define a binary variables. It's about deny. Okay, so in the original dataset, this variable is from S7. So we define if deny equal to 1, if S7 equal to 3, and then deny equal to 0 if S7 not equal to 3, or otherwise. You can use otherwise. Okay, so we use this definition for this deny variable. And next is a PI ratio. PI ratio, we use a S46. It is a debt to income ratio. In the original data, is a percent number, so we should divide it by 100. So we define this PI rate is named PI ratio because rate only 4 characters, but ratio is too long. So I use a rate for this variable name in R. Next, we define a binary variable is black. Okay, so we focus on this variable on the S13. So S13 is a African race. Okay, so we focus on the 3. So black is equal to 1 if S30 equal to 3. Otherwise, black equal to 1 is S13 not equal to 3, or otherwise. Okay, so I use a if-else comment for create the binary variables. If this condition is valid, then this variable is equal to 1. Else, it means this condition is not valid, is invalid, then this variable equal to 0. Okay, so we completely define the variables we want to discuss in this chapter. Okay, so now we discuss some model setting about the generalized linear model. What is the generalized linear model? The generalized linear model is like a regression. Okay, so in a generalized linear model, you should have the 3 components here. Okay, so at first, we should have the random component. What about the random component? Random component, we can use the random component to specify a probability distribution. And this probability distribution, we always use the exponential family, such as the normal distribution, exponential distribution, and so on. Okay, so the purpose of the random component is specifying the probability distribution. Okay, so in next, systematic component is like a regressions, explanatory variables in our model. Okay, so like this, x beta. So here is a matrix form. In a scalar form, you can write down here like beta 0 plus beta 1 times x1 plus beta 2 times x2, and so on. If you use a k regressors, we can plus 2 beta k times xk. Okay, so this is a matrix form here. We define x beta is equal to eta. In the end, we should have the link function to specify the relation between the expected value of y and the systematic component. So we use the link function, like we use the g. This g is a link function. We decide a relation between the eta and mu. And mu is the expected value of y. Okay, so we use the conditional expectation here. Okay, so in a generalized linear model, you should have 3 components. First is a random component, specify the probability distribution. Second is a systematic component. It's like a regressions in your model. And third is a link function. You can specify the relation between the eta, that is the regressors, and the expected value of y is mu. Okay. How about the link functions? Okay, so in this chapter, we use these 3 link functions. The first is identity link. Is a g of mu is equal to mu. It's corresponding to linear probability. Okay, I type it here. Linear probability model. Linear probability model. And the second is a Probit model. It corresponding to the Probit model. Not profit. It's Probit. Okay. And Third is a Logit link. It's corresponding to the Logit model. Okay, so it is 3 link functions we should use in this chapter. Okay, so now we focus on the regression with the binary dependent variable. Okay, so I drink some water. Okay, so in a binary dependent variable, it means no matter y is equal to 0 or 1. So at first, we should calculate the expected value of y. Okay, so write down here, by definition, you can find 0 times the probability with the y equal to 0, 1 times the probability of the y equal to 1, and you can find this term is equal to 0, so we only have the probability of y equal to 1, and we define this term is like a capital G x beta, and here we use a matrix form here. Okay, so we can have the result like this. So here is a transpose. Okay, so here is like a beta 0 plus beta 1 xi1. I is mean observation. Beta 2 times xi2 plus to the beta k xik. Okay, so this is a matrix form result. This is a matrix form. This is a scalar form. Okay, so you can, because of the space in these beamers is too narrow, so I should use a matrix form in here. Okay, so now we discuss some model setting for a linear probability model, Probit model, and Logit model. At first, linear LPM, linear probability models, we use the identity link. So you can find here a capital G with the x beta is equal to x beta. And Probit model, we use the Probit link. It's an inverse normal CDF. So here, because we focus on expected value, so we focus on a capital G. So we use a normal CDF here. Here is a standard normal distribution. The CDF of the standard normal distribution. What is a standard normal? Standard normal is like a normal distribution with the mean equal to 0 and standard deviation is equal to 1, and that is the variance equal to 1. Okay, so and next is a Logit model. Logit model we use the logistic function here. So we use this form. Sometimes some textbook use this form, and some textbook use this form. They are equal to each other. You can focus on here. You can times the exponential with the x beta for the numerator and denominator simultaneously. So you can have this form. And you can, from the right hand side to the left hand side, you can divide it by the exponential x beta at the same time. You can have this result. Okay, so in Logit model, you should focus on the logistic distribution, logistic function here. And in this model setting, we should use we will find this model is a heteroskedasticity. So we should use a robust standard error. Okay, so here we focus on the general form at first. Okay, so if the y is either 0 or 1, then the variance of the y you can find it's like because this is a binary variable. So here is a Bernoulli distribution. So in the Bernoulli distribution, we know it, we recall it, if x is from the Bernoulli distribution with the parameter p, then expected value of x is equal to p, and the variance x equal to p times 1 minus p. So here is like a 1 minus p times 1 minus p, p times 1 minus p. Okay, so we define this term is g, capital G x beta, and this term is 1 minus capital G of the x beta. So we find it. This variance of y is depending on the x. Okay, so it's not constant. So it's not homozygosity. So we should use a robust standard error here. Okay, so now we focus on the linear probability model. Okay, so in the linear probability model, we can, because this is a linear model, we use the identity link, so we can calculate the variance of the error term. Okay, so at first we know in the linear probability model we can use the A1 assumption. So we know. Okay, so recall variance x is equal to expectation of the x square minus the expectation of x half the square. Okay, so you can have this expectation of the x square equal to variance x plus the expectation of x half a square. Okay, so now we transform to a conditional form, like here, such a y. Okay, so now x is a u and y is x. Okay, so we can find this form because in our assumption, the conditional mean of the u is equal to 1. Okay, so here is like, because this term. Okay, so this term is equal to 0. So we ignore this term. And so we focus on this term. By definition, expected value is like a usual real value times the probability and do the summation. Okay, so in this term, y is either 0 or 1. So at first we focus on 1. Plug in the 1 minus x beta have a square and times the x beta, and 0 minus x beta have a square times the 1 minus x beta. Okay, so this is probability of y equal to 1, y equal to 0. Okay, so you can merge these two terms. You can find they have the same term here. Okay, so same term. Okay, so it's like this term. Xi beta. So here is square, so the negative have a double, so negative we can have a positive. Okay, so here's like a cross this two. Okay, in the first turn we can have this turn. Okay, so in this turn is equal to this y minus x beta. First, second, we have a square xi beta. Okay, so here we can do the same thing, xi beta and y minus xi beta, and then we should focus on here plus the xi beta. And this turn we can have a 0, so the result is like this. Okay, so this is exercise 11.8. Okay, so in the regression with the binary dependent variable, you should use the robust standard error. Always, you should use the robust standard error, not use the homoscedasticity standard error. Okay, so we compare these three models. The LPM is easy to use and interpret, but this model setting is not. You should only focus on the between the 0 and 1. Okay, so in LPM, we cannot control the predict value. Okay, so in the values area. Okay, so in the next section, I will demo this linear probability model plot. You can see that this model has some problem. So we usually use the Probit or Logit, not use the LPM, because this model has some problem. We cannot deal with it. Okay, so this is one word. Okay, so I will update a new version after the class. And next, the Probit model and Logit model, we can capture the nonlinear nature of the regression. Okay, so we usually use a Probit and Logit model, not use a linear probability model. And for a result for this page 10, we should use the Heteroskedasticity robust standard error. Okay, so this result is very important. So in your homework, you should use a robust standard error HC1, not use the homoscedasticity standard error by default in R. Okay, so and now we introduce the estimation method. In this chapter, we will use a maximum likelihood estimation. Sometimes we abbreviate this norm at the MLE. Okay, so at first, we should know what is the likelihood function. Okay, so for the likelihood function, we should have a n IID observation. IID means independent identical distribution. Okay, I type it here. Independent identical distribution. Okay, so it's an IID. So, and we have the joint probability distribution. Okay, so the theta is a parameter we are interested, and we have a n observation here, x1, x2 to xn, and we should find a joint probability model, joint probability distribution. So because each term is independent to each other, so we can have a product here to each form. Okay, so because independent okay, sometimes we use this sign. This is an independent sign. Okay, so here is a matrix form. X is mean S1 to Xn. So this term is a joint probability model. And we have the joint probability model, a joint probability distribution, and given capital X is equal to small x. We define the likelihood function of the theta is equivalent to the joint probability distribution. Okay, so in the likelihood function, we want to use the joint probability distribution for data to estimate the parameters we are interested. So here and here, they are different meaning. Here, this x is from the data, and here, joint probability distribution. We use the data have the joint probability distribution. So there are some different concepts, but by definition, we left these two terms is equivalent to each other. Okay, so in a maximum likelihood estimation, we should have the maximum likelihood estimator. So what is the maximum likelihood estimator? We should have the max likelihood function. We can have the theta hat such that the maximize the likelihood function here. And this step is equivalent to we find the log likelihood function at first, and then we also find the maxima log likelihood function. We find the estimator such that we have the maxima log likelihood function here. Okay, so they are equivalent to each other. You can find a log likelihood function, or you can maximize the log likelihood function. They are the same, but we do maximize likelihood function is too complicated. So we always use the log likelihood function because it's easy to do in the programming software. Okay. And next, we introduce the very important property. It's an invariance property, because sometimes we should transform this maximum likelihood estimator to another functional form. So we should have this property to use. If we know the theta hat ML is MLE of the theta. We can find the G function, and the G of the MLE is the MLE of the G of the theta. Okay, so here is mean theta hat is a MLE to the theta, and a G theta is a G theta MLE. Okay, so you can do the functional transformation. For this property, we can very easy to use another form to explain this MLE. And next, we should identify whether MLE is efficient or is useful. So we should have this variance low bound. The variance low bound is named Cramer-Rao low bound. Okay, so what is a CRLB? CRLB is from the log likelihood function, and we can find this is a log likelihood function. We do the second derivative with the theta, and we have the expectation and have a negative sign, and this is the informed matrix of the theta, and we have a 1 divided by the information matrix is defined to the CRLB of the theta. Okay, so this is a lower bound of the variance of the theta hat. It's a lower bound. Okay, so you should know this term is very important. Okay. So for MLE, this term is from the first FOC of the log likelihood function, like this. It's from this term, log likelihood function. If the FOC of the log likelihood function is valid, we know the sampling distribution of the MLE estimator. ML estimator is a asymptotic normal distribution with the mean of the theta, and the variance is the CRB of the theta. Okay, so and this is an asymptotic normal distribution. So it is an asymptotic absolute efficiency. So for MLE, if the first order condition of a log likelihood function is valid, then the MLE is an asymptotic normal distribution. But if the first order condition is invalid, this property we cannot use this property because this condition is not true. For the first order condition is invalid. Okay, so you should check the first order condition at first, and then you can have this property. Okay, and now we focus on the Bernoulli distribution, because in this chapter we focus on the linear probability model, Logit model, Probit model. It's like from the binary dependent variable, so it's a Bernoulli distribution. So we derive the likelihood function, log likelihood function, first order condition, MLE, variance of the MLE, and second derivative, and information matrix, and we find the CRLB is equal to the variance of the MLE. Okay, so at first, we want to calculate the likelihood function here. So at first, we should write down the definition. This is a definition. We have a product of the probability distribution, and plug in the probability distribution. We have a p with the power x to the power x, y minus p, and power is about y minus xi. And we have the take a log. We have a log likelihood function. So by definition, take a log. So product transfer to the summation here, and have a log. And we know log a times b, a with the power a, b with the power b is equal to log a with the power a plus log b with the power b is equal to small a times the log capital A, small b times the log capital B. Okay, so you should know this operation rule for log at first. And then we use this rule to transform this term. Okay, so xi log p plus the y minus xi times the log y minus p. And we use this summation here and summation here. So summation with the 1 is n. And summation here is xi and times the log 1 minus p. So here is the same. Okay, this is a log likelihood function. And next, we do the first order condition, FOC. Okay, so here, how about log p? Log p with the first order condition is a transform to the numerator and denominator. Okay, so here, so we can find summation xi minus 1 minus p, and here is a n minus here, and we should have a transfer rule 1 minus p with the derivative to the p is negative 1, so we should have a negative sign. And here we left this term to the right hand side, so have this term. This term times this term here. This term times this term here. Okay, so we can have this result, MP. This term is this term. We can divide. We can clean out. Okay, so this in the right hand side we can have the p times the summation with the xi, and this in the right hand side, in the left hand side we can have this same term, p times the summation with the xi. So we can have this term. In the end, you should mention that, very important, you should use a capital X, not small x, because it is estimator, not estimate. So you should use a capital X here. Although in this term is a small x, but in the estimator equation you should use a capital X, not small x. So you should use this. You should transform this term to the capital X. So for the MLE of the P is the X bar. Okay, so we find this result. Okay, so maybe you can check this whether this term is unbiased. Okay, if the MLE estimator have an expectation by the result is a EX bar. It's like a mu. A mu is a P. So it is unbiased here. Okay, so MLE for the Bernoulli distribution is unbiased, but in the OLS with the sigma square, it's not unbiased, it's biased. Okay, so it's a famous result. So you can derive it to do the exercise. Okay, so and now we want to find the variance of the MLE. So we can plug in the result. Variance of x bar. So you can find here n p times 1 minus p divided by n. And now we did do the second derivative with the p. Okay, so we first order condition is like here. So we should use this term to do the second derivative here. Or maybe I cannot use. Okay, so this term you can see here to do the second derivative with a p. So here is a p with a power with a -1. So you should time here -1, and here is a p with a square. Okay, so here I should use a square. Okay, so maybe. Okay, so I ignore to type it here. You should have a square. Okay, so now in the next turn, 1 minus p. So the -1 you can plug in here, and to with a power with a -2 in the numerator and denominator with a power 2, and the numerator is the same. And by the chain rule, you also have a -1. -1 and -1 is a +1, so you cannot transform this sign. Okay, so we have a second derivative here, and the information matrix is a negative expectation with the second derivative. Okay, so you can plug in this result here. Okay, so now we calculate this information matrix. Negative is positive, and p with a power 2 is a constant. So here we can find this with the expectation. N is a constant. Negative is positive. N is a constant. 1 minus p with a square is a constant. So we only have this term with the expectation. And this term is equal to n times the p, because we can have the EXI is p because it is a Bernoulli distribution. Okay, so EX is a Bernoulli distribution. So EX is p. Okay, maybe I should transform this term to a capital X. So okay, so I should transform it. Okay, so here we can find this term, np divided by p square, and minus np divided by 1 minus p, we have the square. And you can find here p and p is the result n divided by p, and here is equal to n times 1 minus p. So you can have a one term to delete out n divided by 1 minus p. So you can combine these two terms. Okay, so here 1 minus p times n minus np, n times p. These two terms we can delete, so we have this result. And now we can calculate the CRB. CRB is the 1 divided by the information matrix. So we have a least result. And we can focus on these two terms. The variance of the MLE is this. And the CRB is this. You find they are the same. So it's efficient here. So it is efficient because the variance it meets the minimum of the variance. Efficient. Okay, so for the Bernoulli distribution, the MLE is the efficient estimator. Now we use this result to the general form for the binary dependent variable. Okay, so in the Bernoulli distribution here, the likelihood function here is a p, and here is a y minus p. We plug in this capital G to the p, capital G to the p. Okay, I do the same thing to the likelihood function. And we can also find log likelihood function here. Log likelihood function. Here is a p, and here is also the p. But because the FOC of the log likelihood function is nonlinear, so we should use the numerical method to find the result. We cannot use some formula to do this. Okay, so because it's a nonlinear form, unless it's an identity link. For identity links like OLS, but in another link function, you should use the nonlinear form, so you cannot directly find the result. We should use a numerical method, such as a Newton-Mead or some another method to calculate this result, to estimate the coefficient. Okay, so now we do this. We discuss the first model, LPM, linear probability model. Okay, so the linear probability model, we use the identity link. So the expectation is equal to, we define to the capital G. And by the definition, and we can find, because this is a binary, so we have a expectation of y is equal to the probability of the y equal to 1. Okay, so we have these two terms because we use the identity link. I transform this color. Identity link. Okay. And how can I interpret the coefficient? In our textbook, use the holding constant, the order regressors. You can also use the order thing be equal. Okay, they are the same. Maybe you can use the order thing be equal. Order things being equal. They are the same. Okay, so when the order thing be equal, beta j is the difference in the probability of the y equal to 1 with a unique difference in xj. So, for example, when xi1 change to the xi1 plus 1. What about the change for the probability of the y equal to 1. The probability change beta 1. Okay, so you can use the change for the regressors to interpret the coefficient. How about a marginal efficient? Marginal effect is a partial derivative of the xij. I is mean the observation. J is the non-index of the regressor, 1 to k. Okay, so you have this result because we use an identity link. And now we have an example here. At first, we have a y is a deny, and we use a one regressor pi rate. Okay, so we can use the LPN. You can use the OLS function. It's a linear model directly in R. So but in this model setting, we should use a robust standard error because this result here. Okay, so because this result, heteroskedasticity, we should use a robust standard error here. Okay, so I use this. How can I calculate a robust standard error in R? We should use a sandwich package and use a VCOV HC to calculate the covariance matrix. And we should have a diagonal term and have square root. So it is a robust standard error here. And you should use a type HC1 because in our textbook we use the HC1 type. And next we use two regressors to run the regression. Okay, so we do the same thing, but we change the formula of the model. And in the end, we use the star gather to get the output in the one table. Okay, so this is one regressor model. This is a two regressors model. And we change the standard error here. And we delete the F statistics R-squared, adjusted R-squared, and SER. Because in the linear probability model, this statistic is not important. You cannot use. Okay, so we delete out in the output table. So here we can see if we use the one regressors, this estimation is significant. If we use the two regressors, all regressor is also significant. So maybe we can use this model too to do our analysis. Okay, so next we can have the scatter plot for this model. Okay, so at first we use the run regressors model because if we use the two regressor, we should have the x, y, and x1, x2, and x3, x1, x2, and y axis. So in R, it's not useful to demo this figure. Okay, so I use the only xy. So I use the one regressors model to demo the plot. Okay, so at first I should define that x is a pi rate and y is deny. And x6 I don't use the x because I want to define specificity. And you should choose some setting. and use the label PI ratio deny and a figure title scatter plot of the mortgage application denial and payment to the income ratio. Okay, so and next we should do the axis setting. And 1 is about the x axis, and 2 is about the y axis. And I want to set in this from the 0 to 3, and I want to have a label from the 0 to 3, and they are the same for the y axis. I want to demo the y axis from the negative 0.4 to the 1.4. And next, I want to draw the lines of the regression. So for x value, I want to demo from 0 to 3. And y, I want to use the predict value for this model. So I should input the model. And next, I should use the what's about the x value for the prediction to the prediction. Okay, so I use the steel blue color to the regression line. Okay, so I also use the AB line because I want to do show the 0 and 1 for the horizontal. H is mean horizontal. So you can use a vertical line. If you want to set up the vertical line, you should use the V. H is mean horizontal. Okay, so V is about vertical. Okay, so small h and small v. Okay, so and now we have this result for this plot. Okay, so for the linear probability model, we can find here is greater to 1, here is less than to 0. So it doesn't make sense. So linear probability model has a prediction problem. So we cannot do analysis for this range and this. Okay, so we cannot do the analysis for these two areas. We can only focus on this in the middle area. Okay, so linear probability model has some problem for the prediction because the probability is between the 0 and 1. It's not greater than 1, greater or less than 1, less than 0. Okay, so probability usually between the 0 and 1. I write it down. Probability is not greater than 1, and usually greater than 0. Okay, so here you should note this result. It's very important. How about the predict probability? Okay, so in R, we should, in the textbook, we focus on these two PI ratio. So at first is 0.3 and next is 0.4. Okay, so we can calculate by R predict function. First is a model and input x. Okay, so for the model 1, we have this predict value. In model 2, in for the person 2, we have this value. So and their difference is like this. So we can write down this. When pi ratio is 0.4, 0.3, the PD probability is like this. When the pi ratio is is 0.4, the probability is like this. And you can find they are the difference for this. Okay, so I finished for the linear probability model. And next is a Probit model. How about the Probit model? Probit model is about we use the standard normal distribution CDF. So you can use these two model appearance. Okay, so at first we calculate the expected value of y. We define for this capital G, and because this is binary, so we can find is equal to the probability of y equal to 1. We use the Logit link, Probit link, so we use a Probit link. Okay, so we can find this term, or some textbooks use this. Okay, so they are the same. So, but you should mention that here you should use the inverse function, inverse CDF. Okay, so because it's a Probit link inverse, but it's a Probit link. Okay, so how can I interpret the coefficient? Okay, so if xi1 change to xi1 plus 1, and it's a change the z value, and z value is defined by for these two terms x beta. Is z is like a z x beta. So here z value is like a z x beta. How much the change for z x beta? So it's a beta j. Because the marginal effect in the Probit model is not equal to the coefficient. You can use a partial derivative to xij. You can find, at first we should do the chain rule. Okay, so at first we should do the partial g to the partial z, and next is a partial z and partial xij, and partial z is like a x beta, x beta, x beta. So this term is like a beta. So maybe this term is a beta j. Okay, so and this term CDF to do the partial derivatives, you can find a CDF and PDF. So CDF do the derivative, you can have a PDF. CDF derivative PDF. PDF do the integral. Okay, so you can have a CDF. They are inverse operation. And now, at first we model the one regressors in the model for the Probit model. We use a PI rate. Okay, so now we use a GLM. It means a generalized linear model. So At first, we should plug in the formula. It's same for the LM function. And choose the data set. And now, because we should use the binomial, because we use the regression with the binary dependent variable, and we use the link function with a Probit. Okay, so we also use the VCOVHC command to calculate robust standard error here. And next, we also model the two regressors model, PI ratio and a break. We also input the formula, choose a data set, use a Probit link for the binomial family. We also use the VCOVHC to calculate the robust standard error. And in the end, we also have the output in the one table. We change to these two model and these two standard robust standard error. And we can find this result here. Okay, so in one regression model, we have this coefficient is significant, and two regressors model, you can find these two regressors are also significant. Okay, so in these two model, how can we choose the model in the end to do our analysis? For the model, for the measure of fit, we will discuss the likelihood ratio test, or the fraction of the prediction result, or the pseudo R-squared. We can use these three methods to choose the final model we want to use. So here, I cannot tell you the result, which one we can use. Okay, so and now we also want to have the figure to do the scatter plot to see the pattern of this x and y in the run regression model. Okay, so at first we should define that x is a PI ratio and y is a deny. Okay, so we also label the x and y, and typo of the figure is a Probit model of the probability of a denial given PI ratio. We also set up the axis for x axis and y axis, x and y, and we want to plot the Probit model line and do the same thing. Okay, so and we should choose the type for response because we want to have the expected prediction in for our output, not for the x beta. I want to have the G x beta result. So we can have this result like this plot. So in the Probit model, we can find it's between 0 and 1. So not for the value for the greater to 1 or less than the 0. So this result is valid. It makes sense. So sometimes we use a Probit model. Sometimes we use a Logit model. If you want to very easy to interpret, so maybe you can choose a linear Probit model, but you should mention that you cannot greater than 1 and less than 0 in the prediction value. Okay, so how about the predict probability? At first, you should have the input. It's a model is an input x. Okay, so also we also have a 0.3. Here we have two methods to calculate the prediction probability. At first, we calculate by the CDF of a normal distribution. It's a CDF method. We use a p-norm. T-norm is mean CDF of the standard of a normal distribution. Okay, so here you can use this common directory. And method 2, you can choose a predict function with the response type. Okay, so I think this common is more useful than the p-norm, because you should write down one line. Don't use a two common here. Of course, but the results, they are the same, but it's complicated. But this term is too easy to do in R. And 0.3 is the same. You should only change this term. But this term, they are the same. And you can find a difference by the p-norm or the type response type. Okay, so when the PI ratio is so here when PI ratio is 0.3, the predict value is like this, 9%. When PI ratio is 0.4, the PI ratio is like this, 15%. How about their difference? 6%. Okay, so we can find our result here. So for the Probit model, you can have the two methods to calculate the prediction. The first method is use the CDF method by the p-norm. And the second method is about the, you can also use the predict function, but you should use the response type to set up in the R. Okay, next is a Logit model. How about a Logit model? The Logit model is about we also use the regression with the binary dependent variable. So at first, this term is a definition. Here is a binary, and here because we use a Logit link. Okay, so here we can in some textbook have this term, this form, and in our textbook we use this form, but they are the same. Maybe you can have an inverse Logit link, because okay, so here they are the same. You can transform these two terms here and here. They are the inverse operation. Okay, so here P is about the probability of Y equal to 1. And here, Logit model, we define this term is odds. So his term is odds. Log odds is equal to x beta. This term is equal to x beta. Xi beta. Okay, so here you can very clearly to see the systematic component and the link function. Okay, and next, how can I interpret the coefficient? We do the same thing for the Probit model. So we use a z value here. Z is equal to x beta. So how about when x I 1 change to the xi1 plus 1? The z value is changed for the beta 1. Okay, then the z value z change beta 1. Okay, so because in the marginal effect, you can find a partial derivative partial e partial xij is equal to, we can do the chain rule, partial g partial z partial x. This term, because this is about the logistic function, so we cannot directly use the CDF to the PDF. So, and here this term is also, we have the, because c is x beta, so we can have this term is beta j. And here g partial z, we can have this term. Maybe we can write down the z, gz is equal to 1 divided by exponential negative z. So this term is like this, 1 plus z with a power negative z with a power negative 1. Negative 1, you can plug in here, negative 1. Here is, we can use a negative 2. Do a chain rule. Exponential negative z, I have a derivative to the z. Exponential negative z times the negative 1. And here we can do this form to the numerator and denominator, and plug this term to here. Negative 1 and negative 1 is a 1, so we can do the same thing. And this term is equal to gz times the y minus gz. Okay, so you can check it by yourself. They are the same. Okay, so the marginal effect in a Logit model is like this. And so what is the marginal effect? If x change 1, then the embedding of the y is changed like this. So is x change 1. Here is changed like this. You should calculate this three terms to times each other. It's a marginal effect. The marginal effect is a partial derivative with the xi or xij. And here we also do the same thing for the model set, model demo. At first, we also use a PI ratio. We only change for the link function for Logit. Okay, so, and we also use the VCOV to calculate the robustness error. And next, we also run the two regressors model. So PI ratio and black. We do the same thing for Logit link, robust standard error. And then we export the two model in the one table. Use the stock gather. One regressors, two regressors. Change the robust standard error. Okay, so here we can see this result here. Okay, so this coefficient is significant. This and this also the significant. Okay, so how about the predict value and a scatter plot? At first, we can see a scatter plot. we use the one regressor model as our example. So PI ratio and deny for the x and y, and label here, and have the main title. We want to compare the Probit model and Logit model in a scatter plot. We define the x and y. And we also use the x and y to draw the prediction line, prediction regression, prediction Logit model in our scatter plot. Predict, and we should choose the type for a response because we want to show the probability. That is the GZ, not the X beta. And we also draw another line because we want to show the Probit model, and this term is a Probit model. This term is like a Logit model because I use a different model setting. It's a 11.10. It's a 11.7. There are two model settings. And I want to write down the horizontal line, so use a edge 0 and 1. I want to have a region, Probit model and Logit model. I use the blue line for the Probit model. I use a red line for the Logit model. Okay, so we can see this result here. We can see both the Probit and the Logit. They are between 0 and 1. Okay, not value less than a 0, not value greater than 1. So they make sense. And in the middle area, they are some little different, but we can use this to interpret our interests. So but you can see, because the line range is very small, so their difference is very, very small, not too large. So the result between these two models is close to each other. Okay, so and next is a prediction for the probability. And in the PI ratio for 0.3, you can see here PI rate equal to 0.3. We can also use the P-Logit method. It's a CDF of the logistics function, logistics distribution. And we can also use the predict function directly with the type equal to response. Okay, so and next we also find a PI rate when the PI rate equal to 0.4. We have two methods, P-Logit method and the prediction method with the type equal to response. So difference also have two methods. Okay, so when PI ratio is 0.3, then the prediction probability is equal to 9%. When the PI ratio is 0.4, the prediction probability is equal to 15%. And their difference is 6%. Okay, so you can find this result here. And in the end, we want to have a compare different model. What is our criterion for comparing different model? This topic is about a measure of the fit. So at first, I introduced the likelihood ratio test. This test is not in our textbook, but it's a very useful method to compare the maximum likelihood estimation model. So likelihood ratio test is talking about, at first we should consider the two models. The simple model M0, the complicated model M1. That is the M0 is a special case of the M1. For example, so if the M0 you use one regressors, so use X1. In the M1 model, we use two regressors, S1 and S2. So M0 is only use one regressors in the M1. So we can say M0 is a special case of the M1. And the hypothesis test, we should write down a hypothesis. Null hypothesis is we use the M model 0. And the alternate hypothesis, we use the model 1. How about the test statistic? Here we should calculate the likelihood ratio statistic. So likelihood ratio statistic is like a difference for the deviance. Okay, so and this term is equal to -2 times the likelihood ratio, likelihood of the model 0 minus likelihood of the model 1. And this result is from is asymptotic for the chi-square distribution. And the degree of freedom is the difference between these two models. So you can calculate it by the hand for likelihood ratio. Or you can use the common in R. Here I use the Logit model to do the example. At first, I want to use a model 1 in our null hypothesis. Is use only X1. And a model 2 in the alternative hypothesis, we use two regressors S1 and S2. And we choose the significant level be the 5%. In R, the LR test function is in the LM test package. So you should library this package, LM test. And here, write down the model 0. Here is model 1. Model 0 is simple. And model 1 is complicated. Okay, so here you can find the result here. The test statistic is about 68.798. And the p-value is less than 0.1%. So it's very significant. So we can write down a conclusion. Because the p-value is less than 5%, we reject the null hypothesis. We decide to use the model 2. That is we use the two regressors in our analysis. And next, we can use the fraction correctly predicts. It's in a machine learning, we use the that is the confusion matrix. They are the same. Okay, so although they are the different name, they are the same thing. Okay, so here we can see the confusion matrix as the follow. This table, you can see here, it's an actual y equals 0, y equals 1, And here is a predict value, y equals 0, y equals 1. And this term t0 is mean true predict for 0. T0 is mean true predict 0. And F0 is mean false predict 0. F1 is mean false predict 1. T1 is mean true predict 1. Okay, so this is a confusion matrix. By the confusion matrix, we can calculate the fraction correctly predict. The numerator, the denominator is about all term. T0 times the T1 times the F1 times the num times plus T0 plus the T1 plus the F1 plus the F0. And the numerator is about the T0 times the plus the T1. Okay, so in the numerator is a diagonal term, sum of the diagonal term. Okay, so although this is easy to understand, but we cannot see the quality of the prediction. So sometimes it's not great to our analysis. So, but in the first time, we can use these two terms to do our analysis for choose some model. But you can see, but sometimes the result is the same for the likelihood ratio test, and next topic is about pseudo R-squared. Okay, so we can see our example for a logic model. How can we find a confusion matrix in R? You can use the REG class package here. And in this package, we can have the confusion matrix function. And you can plug in the model here. So you can find this is a confusion matrix. For the one regressor is the S1. Maybe I think it's the PI ratio. So you can find in total observation is 2,380. And the true predict value is observation is about 2,089 plus the 11. So you can find the fraction of the correct predict is about 88%. And if we use the two regressors, PI ratio and the BRAC, we find the prediction correctly is increased a little. Okay, so it's about 88%, 88.27%, and at first it is 88.23%. So you cannot do some tests to say they are different, because they are close to each other. So we should use another criterion to say they are different. Okay, so next is a pseudo R-squared. What is a pseudo R-squared? It's based on the maximal likelihood function, maximal likelihood estimator. We want to do the same thing to the concept of R-squared in the ordinary least square. In the OLS, we use the R-squared or adjusted R-squared to say to do the measure of the fitting. In in the model with the maximum likelihood estimation, we cannot use the R-squared directly. So we should use the pseudo R-squared. Pseudo R-squared means it is defined by y minus the numerator is about the log f max. It means we including all the x we want to use. And the denominator is about a normal model log likelihood. So like likelihood take a log. So we can find this term is excluding all the x. That is the only include intercept. So I use this for the Logit model to take our example. In the past, we use one regressors and two regressors model. So now we should fit the null model. Only have an intercept at first. So in the null model, we should deny tilde 1. 1 is mean only intercept. Okay, so and we use the same logic link for a binomial family, and we calculate the pseudo R-squared by hand in R. We should find a log likelihood for the full model divided by the null model log likelihood. We find the pseudo R-squared is about 4%. 5%, 4.8%. It's for the only one regressors, PI ratio. If we use two regressors, the pseudo R-squared is like 8.7%, 8.8%. So they are different. So in the model 2, it's great. Pseudo R-squared in model 2 is greater than the pseudo R-squared in the model 1. So we should use the model 2 regressors to do our analysis. In pseudo R-squared, we do this conclusion. In the fraction of the correct predict, we do the same conclusion. Because this prediction correctly is great in the model 2 is greater than the model 1. So we should use the model 2. In a log likelihood ratio test, we also have the same result, same conclusion. Okay, so because the p-value is less than the 5%, so we should use the model 2 to do in our analysis. Okay, so in this chapter, in the end, we take a quick review. Okay, so in this chapter, we should focus on something. At first, model setting. Okay, so you should write down the link function or the s beta EYX equal to G X beta plus equal to Y equal to 1. Probability of the Y equal to 1 given by X. And for the LPM, Probit Model, Logit Model. So second is the LPM, Probit Model, Logit Model. And you should use the robust standard error. Robust standard error. Okay, so and know the beta J meaning and know how to predict. Okay, so and you should know some advantage. What this advantage pros and cons for each model. And third, you should know the model of fit, measure of fit. Okay, so that's all for this chapter. Okay, so I think I finished for, I think I do a very completed introduction for the GLM, generalized linear model.